Okay, thank you, Sergey, and thank you, Barbara, for inviting me in this prestigious place. And so I will try to show you what we can say about LAB, lithosphere, asthenosphere boundary, by using anisotropy. And so I will start by this review figure by Heaton. He showed that this kind of concept, lithosphere, asthenosphere boundary, is quite elusive, and we have different ways to investigate this kind of boundary by using different kind of geophysical parameters. And for example, if you consider the mechanical lithosphere, we find something which is usually quite small, between 30 and 50 kilometers. If we consider the thermal lithosphere, we have a slightly thicker lithosphere, and the LAB might be located at larger depths. What I will focus, of course, is about seismological information, and we have different ways to look at seismic information by looking at S-wave velocity, and usually we find that we have a decrease of velocity at the lab. And I will focus on seismic anisotropy. I will show you that we can also get some information about lithosphere and LAB by using seismic anisotropy, and some people are also using electromagnetic data by looking at the conductivity or resistivity. And so different ways from seismic waves, seismic data to address the issue of LAB. Of course, we can use receiver function, we can use surface waves, and there are some different estimates. If you look at the figure by Ratchert or by Kawakatsu, but it's not at the global scale, but from Ratchert, you see that we get something which is not very deep in terms of LAB compared to what we get from surface waves. So we have really a problem of discrepancy between this kind of data, and at the global scale, we have also other information by using heat flux. That's a figure from Artemieva, but as you can see, most of the information are below continents and very few below ocean. So I will focus basically my talk on oceanic areas. And as I mentioned, we have discrepancy between different estimates of LAB, and surface waves provide continental routes down to 200, 250 kilometers, whereas receiver functions provide smaller depths. And it was proposed by Johann and Romanowicz that what people see is not exactly the LAB at 80 kilometers, but we have some intermediate mid-lithospheric boundary, which is located in the middle of the continent. And it is, I guess, a way to reconcile different kinds of seismic data, and I will show you that what we get for oceans is also we need more complexity than one is usually believed. So I use two different approaches from surface wave dispersion. First of all, by using only S-wave velocity, and with students we look at some Monte Carlo approach. We have to explore the parameter space, which in this case is composed of the depth of the lab. You see, we have a start. We explore the lab delta Z1, and we try to see how to explain seismic wave dispersion. And from another technique, we are using first-order perturbation theory. In that case, we have a gradient, and we assume that if we filter this kind of function, of Heaviside function, the maximum of gradient is related to this lab. So it is a maximum of gradient that we consider, and we consider that it is a good proxy for the LAB. We can also try to look at other parameters, and of course, seismic anisotropy. When we consider tomographic models, we have 4 well-resolved parameters. We have the SV wave velocity, the radial anisotropy, which is the ratio between VSH and VSV, and we have azimuthal anisotropy, which express the azimuthal variation of VSV velocity. And we consider two different results. It is two examples at different locations, one in below ocean, the other one below a continent. And what we see for oceans, we have well-defined gradients for VSV and also for Xi parameter. It's a bit more complex for G parameter, but we also have the strong gradient. And very often what we observe is a change in the orientation of azimuthal anisotropy with depth. And so you see that we can get different estimates of something which might be a discontinuity, which might be the lab or something else. For continents, it is usually much more complex because you see that we have this gradient here, but the low velocity zone, which is usually very visible for oceans, is not so visible for continents. And so we have some estimate from VSV, but from radial anisotropy, it's much more complex because we have a maximum, which is at about 100 kilometers. But what should we consider as a lab? Was because there's this maximum of gradient here or the minimum of gradient here. It's much more difficult. It's the same issue for azimuthal anisotropy, where we have also different estimates of the lab which are possible. And so it's much more complex for continents than for oceans. And so let me first remind some basic results about general approach by using seismic anisotropy. And what we have to realize is that seismic anisotropy is the rule, not the exception. It is present at all scale, from the microscopic scale up to very large scale, macroscopic scale. But the main problem is that we have different processes, different mechanisms of alignment of minerals in the crust and in the upper mantle. We have lattice preferentiation, LPO. We have shape preferentiation with fluid inclusion of cracks, and we have also fine layering. And let me show you some example of these three processes. And so we are faced with the problem that we have some observed anisotropy, but non-unique interpretation. And that's the main difficulty when we are observing seismic anisotropy, is the interpretation, which is not unique, and probably we have different processes in different layers. And it is, I detail here the different processes. For example, if you have a shape preferentiation, we have distribution of cracks. That's a figure from Babushka and Kara. And when we have a stress field and a compressive stress, you tend to open the cracks or the fluid inclusions in the direction of the compressive stress and to close for orthogonal orientation. Okay, so this kind of mechanism is sensitive to the stress. The most popular interpretation is usually through LPO. Most popular interpretation of anisotropy is through LPO, which means lattice preferentiation. If you consider, for example, olivine, the fast axis of olivine, maybe you don't see, but it's about 10 kilometers per second, tends to be parallel to the flow direction. And the slow velocity is perpendicular to this flow plane here. And so you see that for seismic anisotropy, by the way, you see it's between 8 kilometers per second to 10, so it's very large. It's about 20%, so it's not a negligible effect. And the main application of this observation is that we are able to map the flow inside the mantle if we are able to retrieve the fast velocities within the mantle. We have a last process which can give rise to seismic anisotropy. It is the fine layering. If we have a stratification, the layering of thin layers, much smaller than the seismic wavelengths, the effective medium will be anisotropic. In that case, if you have horizontal medium, it's a specific case where we have what we call a VTI medium, and we have only 5 parameters, but it was demonstrated that we can give rise by this kind of stratification the correct amplitude for the difference between VSH and VSV, which is related to the radial anisotropy. And so that, we have 3 processes, and even we can add some complexity if we take account of the fluid content, for example, but you see that we have a lot of information in seismic anisotropy. Of course, we have information about present-day tectonics and geodynamic processes, and even on past processes by looking at the frozen anisotropy. So it is quite difficult to separate the different kinds of anisotropy in different layers because we will have different interpretation, but it can be very rewarding because we'll have a lot of interesting information. And so what we will try to show you is that we have a stratification of anisotropy in the crust and the mantle. And we can wonder what's about the lab with respect to seismic anisotropy. Okay, so to observe anisotropy, we need data, and we have used different kinds of data. We have used, for many years, body wave data and the classical effect of birefringence. When you have a wave which come into an anisotropic medium, it splits into two S waves with orthogonal polarizations and with different velocities. And so outside the medium, you have two waves with a delay time and a specific orientation. So it is used for many years. And we have also information on anisotropy from surface waves, and we can use two kinds of surface waves, Rayleigh and Love waves. It is known for at least maybe 50 years that there is a discrepancy between Rayleigh and Love waves when you use an isotropic medium, so you need to introduce radial anisotropy, what I named the VTI model. And we also have for the dispersion curves of Rayleigh and Love waves some azimuthal variation of phase or group velocities. There are some other effects I will not mention today, but which are quite promising, is to look to amplitude effect and to investigate quasi-Rayleigh wave and quasi-Love wave, but it's another story. Okay, so I will focus basically on these two kinds of observation, Rayleigh-Love discrepancy, azimuthal variation of phase and group velocities. And that's only I only show this equation to give you some flavor of what we do from a theoretical point of view. I don't want to detail. Usually seismic anisotropy is expressed through an elastic tensor. I know it scares students usually because it's a fourth order tensor, so we have to calculate this kind of product to obtain the phase velocity of Rayleigh or Love waves. And the result is quite simple. If we consider the phase velocity perturbation at a given point as a function of the azimuth, we have to do Fourier series expansion as a function of psi, the azimuth along the path. And we need 5 terms because since we have a fourth order tensor, we have to consider not only the 2 psi term, but also the 4 psi terms. And we have from this, if we can retrieve these different alpha terms, we can have information about different parameters. And as I told you, in the general case, elastic tensor, it's quite complex because we have 21 independent elastic moduli, but actually we can only retrieve some of them. So I don't want to detail everything here, but basically the red parameters are the parameters we can retrieve from surface wave tomography. So we can have access to the VSV. We have access to the radial anisotropy, which is the ratio between VSH and VSV. And we have also access to azimuthal anisotropy of VSV. And by the way, these parameters can be very useful because they can be related to SKS splitting by using a simple calculation. But again, it's only to show that we can make comparison between surface waves and body wave anisotropy. Okay, so let me go back to seismic anisotropy and what we will do. So, as I told you, from seismic anisotropy, we have access for oceans to these different strong gradient, and we are using these strong gradients as proxy for lab or something else. And I will forget, but I will show you over some results for continents where it is much more complex. Okay, so we use data from different origins. We are using, of course, data from IPGP, from Utrecht, and Jeannot Tremper provided the different data from Harvard, from Boulder, Mike Ritzwaller and Nikolai Shapiro provided all this data. So we have phase and group velocity, so we have a lot of data, and we have some good azimuthal coverage that I don't show here. And so what we do, we regionalize the phase velocities, which are calculated along all this path, and we obtain this local dispersion velocity at different periods. Basically, when you have a short period, not so short, but at 50 seconds, you are sensitive to the lithosphere, and when you go at longer period, you are sensitive also to the asthenosphere. And I show two examples of phase velocity dispersion curve for Rayleigh and Love waves. And what we obtain is basically an agreement with what we expect from seismic data. I mean, we saw slow velocities for ridges, high velocities for old areas such as shields, and we also can see the orientation of azimuthal anisotropy, which is in good agreement with plate motion. And so we have some confidence about this phase velocity map. In a second step, and that's a step which will give us access to the lab, we use two different techniques. We use a statistical Monte Carlo inversion and a first-order perturbation theory, and from this phase velocity map. And for the Monte Carlo inversion, as I told you, we explore the parameter space. It's only an isotropic Monte Carlo inversion. And when we do that, we have access, you see, to Z lab, which is actually the depth of this discontinuity here, and we have access also to the velocities in the lithosphere and in the asthenosphere and even deeper. And it is what we get. And so we get, again, a classical map of the lab, and with a thin lab around ridges, with a thick lab in old shields, and so on. And we have also the velocities, again, which are reflecting basically the thermal state of the lithosphere. Okay, so now from first-order perturbation theory, we do an inversion, and we obtain, again, at different depths, these different maps between 50 and 300 kilometers, and azimuthal anisotropy. So we see that we have a small anisotropy, it's only 2%, but it's quite significant. And from these different maps, we can also extract the lab by using this approach. As I told you, we look at the gradient of VSV, we look at the gradient of radial anisotropy, gradient of G and psi G, and I will only show you the result for psi on oceans, but for VSV we have do the inversion for everything. And so that's we obtain from the gradient of VSV. So we consider the maximum gradient, and that is the map that we obtain. And again, we have a very similar patterns, but if we, okay, I would like to move to this one. If we look at the comparison between Monte Carlo inversion and first-order perturbation theory, for oceans we had very good agreement. For continents, it's not so evident because actually we tend to have a thicker lab when we are using first-order perturbation theory. And the reason is that in the Monte Carlo inversion, we do not take account of radial anisotropy in the lithosphere and asthenosphere, so it's only an isotropic inversion. So we think that the discrepancy between lab derived from VSV and lab derived from Monte Carlo inversion is due to the neglect of radial anisotropy. But we have the same lateral variation. So we have not the same absolute value, but we have the same lateral variation. So let me go back now to psi. That is probably the most surprising results when we consider the maximum of gradient of psi, the radial anisotropy. We obtain something only for ocean, but which is quite uniform. You see that except we see the ridges, but in most of the continents we have no lateral variations of this something which must be a discontinuity, and that is something we try to work on. Now, if we consider azimuthal anisotropy, we can also use the difference of orientation between plate motion and orientation of azimuthal anisotropy, and we can see how this azimuth is varying. And what from the change in the orientation, we find that we can have also access to something, a proxy of the lab probably, and I will show you some maps. But it doesn't work everywhere because in some places, for example in young oceans, we have no depth variation, so we cannot have access to the lab from this information. So that's what I showed you, and now that's a a map where we show for the half-space cooling model, so it's only a thermal, very simple model, and we saw results for what we call the lab, for VSV velocity for ocean, VSV velocity by first-order perturbation theory, and the XI, the radial anisotropy, and the azimuthal anisotropy. So what we can see that basically for Monte Carlo inversion, we tend to have something which is flattening with the age of the seafloor. We have here between 0 and 175 million years, whereas when we incorporate anisotropy, we have something which is in better agreement with a specific isotherm. For azimuthal anisotropy, again, we have, you see, it's quite scattered data, so it's not as good as for VSV, but we have something which is also flattening, but it's not so evident. The most interesting results regards this discontinuity here, obtained from the radial anisotropy. You see that it is increasing very rapidly, and afterwards it's almost flat at about between 60 and 80 kilometers. So we don't have this thickening for this parameter. And what we did the same plot, but now we are using a plate model. It is a plate model of Mackenzie in 2005. In that case, we see that it's not so different, except that for there seems to be some slightly better agreement about the younger age, but not for the older ages. And of course, we can, for radial anisotropy, we can imagine that we have also this some kind of agreement if it is the lab. And what we observe is also for the Pacific Ocean, it can be also obtained for the Atlantic and the Indian Ocean. In that case, we have a better agreement with the Mackenzie, the plate model. You see here that we have some result which is in good agreement with the isotherm of 1300 degrees. And for Indian Ocean, again, we have some good agreement. And again, it is even more flat. The discontinuity obtained from radial anisotropy is quite flat, between around 60 kilometers for Atlantic and Indian Ocean. So we can really wonder, so that's my first conclusion. I still have 5 minutes, that's fine. And so what we observe is that we explore different proxies by using S-wave velocity and anisotropy. And for the duration from VS, we find the same lateral variation of lab between isotropic and anisotropic inversion, but a different absolute value, which is due to anisotropy. And if we consider the radial anisotropy, we see that we have a different image. Now we have something which is almost constant, and the age variation is very small. And so we have to revisit what's going on and why do we observe this discontinuity or this strong increase, because actually we are inverting for a strong gradient. Why do we have this observation, which is very different from what we obtain from S-wave velocity? And so I will rapidly show you some results we obtained for the Horn of Africa. Of course, it's not exactly a ridge, but it's where we have some opening plates. And so I will show you some results obtained with Matthias Obrebski and Lev Vinik by using receiver functions. And in that case, what we try to do in this work is to simultaneously invert SKS and receiver functions, and so in the anisotropic framework. And what we obtain is this kind of results. So it's, we use a gyroscope station of Djibouti, ATD, and here are the data, receiver function, SKS data, and what we see is, again, a statistical approach where we try to invert for VS velocity. Alpha is the amplitude of anisotropy, and we have the azimuth. And so what we see for this station is that we have a stratification of anisotropy with different orientation and different amplitude. And if we try to interpret the stratification, we can say that we have in the upper part down to about 30 kilometers, a very small anisotropy compared to a small layer around 40 kilometers, which is probably related to partial melting down to about 45 kilometers. And when we go deeper, we have a different orientation. You see the jump in the orientation, and we have about quite strong anisotropy down to about 120 kilometers. And so we believe that in that case we have more something related to SPO, so shape prefer orientation, probably fluid inclusions. And when we go deeper, more anisotropy related to LPO. And so it was a tentative interpretation of this kind of data. Of course, it's a cartoon, and what we try to show is that we have different layers with different orientation. In the top layer, we have something which is about north-south. When you go deeper, we have something which is more corresponding to the relation between the Hafar hotspot and the Gulf of Aden here. So we see that we have different layers with different interpretations and with different orientation. And so that's also a cartoon I tried to do yesterday evening. And I tried to explain why do we have this kind of a strong gradient in the middle of the lithosphere. And we have to go back to how we form the lithosphere at the mid-ocean ridges. And of course, we have some upwelling, and we have some zone with partial melting. And of course, we have a lot of small-scale convection in this part, and probably in the upper part of the lithosphere, we have wavelengths of anisotropy which cannot be observable, and so we have some incoherent large-scale anisotropy. It does not mean there is no anisotropy. It means that since we are only looking for long wavelengths, we cannot see it in the upper 40, 50 kilometers. Now, if we consider the deeper lithosphere, we have something which is more coherent, and probably what we observe in this bottom part of the lithosphere is some fossil anisotropy, and due to lattice prefer orientation. And in that case, we have an increase of the radial anisotropy. And finally, we have here the thermal LAB, which is due to the cooling of the lithosphere. And below LAB, we have the Asthenosphere with the mixing of LPO anisotropy and partial melting. For example, the model of Kawakatsu, the millefeuille model. So in this part of the upper mantle, we have different processes giving rise to seismic anisotropy. So what I wanted to show you in this simple cartoon is to show that we have different layers. We have the stratification of anisotropy, different processes, and what we try to do is to try to understand this kind of different processes by using, at the same time, SV velocity, which give access to the lab, to the thermal lab, and radial anisotropy, which give access to this mid-lithospheric boundary, which is not well defined, but which seems very constant with age. So to conclude my talk, what we showed you is that, okay, for ocean, the half-space cooling model doesn't work very well, but the plate model of Mackenzie works slightly better. It's not perfect. It's slightly better, at least for Atlantic and Indian Ocean. And we try to propose a tentative explanation for this radial anisotropic proxy, strong gradient, which is in the middle of the lithosphere and which can be derived from Xi. And now the next step will be to apply these different techniques to continents, but it's another story. And thank you very much for your attention.